Thank you so much for the introduction, and thank you to everybody for coming out here. I know a lot of you guys have come from very far, and to everyone online tuning in from across the world, thank you so much for being here. So yeah, today I'll be discussing the topic of my master's thesis. This is the past 2 years of work I've been doing on the structural controls on gold mineralization at the Great Bear property in Red Lake, Ontario. So quickly before I begin, let's see if this will actually do that. I just want to say a quick thank you. So this research was done at the Mineral Exploration Research Center at Laurentian University, and it was in a partnership with Kinross. So funding was provided by an NSERC Alliance grant, which was generously matched by Kinross, making this research possible. So let's start with the story of Great Bear. So the Great Bear deposit is located in the Red Lake Greenstone Belt in the Uchi domain within the Superior Craton. So we can see an outline of the Superior Craton here. It extends through most of Ontario and into Quebec with minor amounts in the province of Manitoba. The Uchi domain is located here, bounded to the north by the North Caribou Corps and to the south by the English River. This box here in red corresponds with this map to the right. So this map is of the Red Lake Greenstone Belt. Now, the Red Lake Greenstone Belt is very well known as it's produced over 30 million ounces of gold to date. Now, those mines are shown both historic and active mining within these numbered points here. And these numbered points here define what's called the Red Lake Mine Trend. All good? Too much light? Oh, I think, well, the sun. Anyway, okay, I'm just gonna keep going. So the number of points here, they define what's called the Red Lake Mine Trend. The Red Lake Mine Trend hosts, these mines are all hosted within Mesoarchean rocks, so we're talking much older lithologies. And the Great Bear property is unique in that it's located 25 kilometers southeast of the municipality of Red Lake and the Red Lake Mine Trend, and is hosted in considerably younger lithologies. So regional mapping compilation done in 2004 by Sanborn Berry states that this beige unit here is the Neo-Archean Confederation assemblage rocks. And to the south here, we have what was mapped at the time as unknown supracrustal assemblage. So as you can see, there hasn't really been a lot of interest in this area because it was always considered to be younger rocks, and they always thought it was too young to be mineralized. Well, in 2017, Great Bear Resources and Rumini were doing exploration in the area. And in 2019, they drilled the discovery drill hole into what is now known as the LP zone. And from there, they intercepted over 100 meters of mineralization, and the rest is history. If we cut forward to September 2024, the deposit contains a measured and indicated gold resource of 2.7 million ounces at 2.81 grams per ton, as well as an inferred resource of 3.9 million ounces at 4.71 grams per ton. So since the discovery of the LP zone, and the LP zone contains 95% of that gold resource, in early 2019, there's been just a huge amount of academic interest in the deposits. So this research is actually one of 4 ongoing graduate studies on the deposit. So current research aims to characterize the mineralization, determine the pressure temperature conditions across the deposit, and provide a more detailed lithostratigraphy of that mafic domain. So this research that I'll be presenting on today aims to be the first comprehensive structural interpretation of the deposit. And it means a lot to me because I actually previously worked on the deposit. I worked for Kinross for a year. I was core logging, and I had an amazing time there. And when the opportunity arose for me to further study the deposit, it was an absolute joy. So this is actually, as you can see, the property from my first field season there. And you can see that there is significant cover on the deposit, which kind of explains why it might not have been as well known. But this is actually from fall of last year, so there's been even more development. As you can see, they're really going hard to better understand the deposit and push forward with going into the advanced exploration stages. So it's really the time in which we need to understand the deposit better. So the question seems fairly straightforward. What are the structural controls on gold mineralization at the Great Bear deposit? Well, to understand that, we have to answer some of the questions first, like what structures are even present on the deposit? How can we interpret the structural history from these observations? Finally, when did gold mineralization actually occur? And what is the relationship between that gold mineralization and the structural history? And then finally, we can put all of this into the regional context. So I was able to determine this using a mix of outcrop and regional mapping. In total, 9 outcrops and mechanically stripped outcrops were mapped as part of the study. And then this was supplemented by the logging of oriented drill core, as mineralization doesn't actually outcrop at surface. So we looked at drill core to better understand the relationship between these structures and mineralization visible at depth. This was then supplemented by petrography, looking at things like microstructures and microtextures to supplement what was seen on the outcrop scale. And then finally, uranium lead zircon geochronology to provide brackets on that deformation and mineralization. So the presentation is going to follow the following outline. Quickly, we're going to go over the deposit geology to understand the deposit a little bit better before getting into our structural overview and interpretation. Then we'll finally get into the timing of that deformation and the regional context. And then we'll get into the timing and structural controls on the gold mineralization itself before ending with some closing remarks. So let's get into the deposit geology. So this is the claim outline shown in black here, and this larger map is shown by this orange box. So the Great Bear property is divided into 2 domains. There is a northern felsic domain and a southern mafic domain. Now, this northern felsic domain is a felsic volcanosedimentary sequence deposited in a marine basin. It's a sequence of different metasedimentary units shown in grays, the last one being intercalated with felsic lapilli tuffs, and large voluminous intrusions of quartz feldspar porphyry and less quantities of an apheric, often sometimes feldspar-feric porphyry. And then in the south, we have the mafic domain. So that's iron and magnesium tholiatic rocks, a lot of foliated mafic flows, pillows, and some what appear to be massive units. And we also have few cherty argillites in there, as well as some ultramafic flow horizons. Now, these 2 domains are separated by what is called the geophysical LP fault. Now, the LP fault was identified by Zhang and Calvert in 2006. It was identified in seismic structures. It's LP for lithoprobe. And it's an 18-kilometer structure that was projected to a depth of around 12 kilometers. And it really separates these 2 deposits. And it's not really visible in core as, say, like a discrete brittle feature. And we'll get a little bit more into what the deformation actually looks like in a moment. But what we should note is the location of mineralization. So first we have the LP zone, which, as you can see, is located within the felsic domain here. And it has a strike length of around 4.5 kilometers. It can be up to 400 meters wide to a depth of around over a kilometer. Next up, we have the limb zone, which is hosted within the mafic domain, within argillites here. And it is considerably narrow, around 10 to 15 meters wide, and hosting considerably less of that mineralization. And then finally, we have the hinge zone, which is located within its quartz carbonate veins in the hinge of this regional fold in those mafic volcanics. So I find it's often best for us to look at things in 3D. So why don't we take a look along this cross-section line here? So in cross-section, we're able to see a little bit better the geometry of some of these units. So what we can see here is the mafic and felsic domains. And what I want to highlight is these foliation form lines, which show not only that we have a very strong northwest striking, northeast dipping fabric, but also these form lines, their spacing correlates with the intensity of the fabric, which and also the intensity of the fabric can be seen by this gradational line here. And what I want to highlight is what's called the LP deformation zone. And this is the deformation zone that affects the property. So what we have is a deformation zone that is really characterized by this strong flattening fabric seen across the property. And we see this deformation is strongest within a 500-meter corridor around the center of the felsic zone, or around the felsic domain, but is over 1.5 kilometers in like full width. Its boundaries are difficult to define because of the nature of the fact that we do not have significant outcrop, and also the fact that the deformation tends to grade out as we get further from that geophysical LP fault. Also on here, I want to highlight the red shapes we have here show the mineralized zones of the limb and LP zone. These were as proven by drilling when I first started the project, but what I really want to highlight is that the mineralized zones are now parallel with that strong flattening fabric. Now, why don't we take a little bit of a closer look at what each of these lithologies actually look like. So this is the lithologies of the mafic domain. So we have those high iron tholiates are usually our well-foliated mafic flows, our pillows. And what we can really see is we have a high concentrations of that chlorite and carbonate alteration, as well as a high propensity of those garnet porphyroblasts. What we also have in the mafic domain here is these high magnesium tholiites. They often tend to be more massive. What we're commonly seeing is a high concentration of hornblende, which has a tendency to overprint the dominant foliation. And then finally, we have these argillites, which are dark gray to black, very fine grained, and have high concentrations of exhalative pyrrhotite. Next up in the felsic domain, this is our felsic volcanosedimentary sequence. So we have three distinct metasedimentary units, starting with what's called the MS3. So this is our felsic siltstones and sandstones. Bedding is quite variable, but we often see high concentrations of sericite alteration. Overlying this is the MS2, which is more siltstones and always sort of defined by this metamorphic assemblage, including garnet, staurolite, and andalusite. The final metasedimentary unit is this felsic siltstone that is commonly interbedded with this quartz feldspar ferric lapilli tuff. Now, this lapilli tuff often contains clasts or fragments of this quartz feldspar porphyry, indicating that they are genetically related. Now, this quartz feldspar porphyry is the most voluminous intrusion on the property. It contains, it's often defined by its large quartz phenocryst and commonly displays a myelinitic texture. It is commonly mineralized, as is the apheric felsic porphyry, which is another intrusive unit that often has feldspar phenocrysts that have been altered to albite. All right. So now that we've gone over the geology, let's finally get into the structures, the fun part. So there's one thing that we need to go over. Actually, we're going to have a couple of topics and concepts that we're going to introduce as we go through the structural geology. And the first one is transpression. Now, transpression is a type of deformation that results from simultaneous compression and transcurrent movements. So this means that we have deformation resulting from simultaneous strike slip or simple shear movement parallel to deformation zone boundaries, and shortening or pure shear perpendicular to those zone boundaries with a vertical lengthening along the shear plane. So what this means is we have fabrics that are developed from both the pure shear and simple shear components as they're combined. And so we have the formation of a strong flattening fabric. And within the vertical plane, we'll have the development of a mineral stretching lineation, which will be elongated in the direction of the extrusion direction. Notably, we will not see any asymmetry as we have just extension. Meanwhile, on the horizontal plane, we'll have the development of certain shear sense indicators, so things like asymmetric strain shadows, shear bands, or perhaps asymmetric folding. All of these will be contained within that horizontal plane. Now, let's get into what we actually see on the the outcrop scale. So we're going to start with the Vigo outcrop. As I mentioned, there's a lot of, we did mapping of 9 outcrops, but of course, for time's sake, we can only describe a few. So we're going to start with the Vigo outcrop. This is located in the felsic domain, just about 100 meters north of that geophysical LP fault. The boundary between the two domains is within the heart of the LP deformation zone. Now, it hosts mainly quartz feldspar porphyry with quartz feldspar ferric felsic tuff and some minor siltstones. It is dominated by a very strong early myelinitic foliation. I use the term early foliation, or SE, as it is the first foliation that we see. It helps with a little bit of confusion as opposed to using S1, S2. We'll start with SE. So this foliation dominates the outcrop. It is northwest striking, steeply dipping. We have the flattening of quartz phenocrysts along this fabric, which helps to define it. We also have quartz veins that are isoclinally folded, and the early foliation is axial planar to these folds. Along this foliation, on the few vertical surfaces that we do have, we see that we have the weak to moderate stretching of quartz phenocrysts. Here they're outlined in yellow because they're a little difficult to see on this image, but we have the stretching of those quartz phenocrysts, defining a steeply plunging mineral stretching lineation. Now, what's more interesting on this outcrop, though, is that we have consistent dextral asymmetry, which is extremely cool. We have the recrystallization of those quartz phenocrysts and the development of these asymmetric tails on those phenocrysts. We have dextral shear bands, which transect mafic dikes, as you can see here. And we also have the dextral shearing of these quartz tourmaline veins within the dikes themselves. We have this coeval oblique foliation within these amphibole dominant or hornblende dominant dikes. And then finally, we have these late Z folds of chlorite-rich mafic dikes. So you can see this is an asymmetric fold. There's folding of the foliation within the host rock. And then there's also the development of an axioplanar fabric, an SL fabric, within those dikes. So we see these fabrics not just at the Vigo outcrop, but across the felsic domain. But what's interesting is we also see them within the mafic domain. So this is at the Inco outcrop, which is located almost along the boundary between the mafic and felsic domains, and we see primarily mafic lithologies, but some quartz feldspar porphyry. So at this outcrop, we see that same strong early foliation, northwest striking, steeply dipping. Its orientation is still parallel to the orientation of the geophysical LP fault at this point. And we also see that same isoclinal folding or tight to isoclinal folding of this intermediate dike. We have here a mafic dike within the quartz feldspar porphyry. It has been dextrally sheared, and we actually see that rotation of the early foliation into the dike, indicating that shearing. And then finally, this is actually a cross-polarized microphotograph of a quartz phoenochorus that has been recrystallized. You can see recrystallization of the grain, and you can also see that dextral asymmetry. So along these asymmetric quartz phoenochorus, once again, we see that they are elongated in the vertical plane, once again suggesting that we have, and indicating a steeply dipping mineral stretching lineation. So all of these structures come together to suggest that we may have a single long-lived dextral transpressional event. So let's break down exactly which of those structures actually gives us this indication. First is that coeval oblique myelinitic foliation in those competent mafic dikes that are themselves oriented parallel to the myelinitic foliation in the surrounding rock. Very telling is the deformed quartz phoenochorus with dextral asymmetrical strain shadows on horizontal outcrop surfaces that are vertically stretched on vertical outcrop surfaces. And finally, what's very cool is the fold axes of those early isoclinal folds and the later Z-shaped folds, along with the mineral stretching lineations, are all rotated into parallelism, and they are all steeply plunging, indicating that we have concurrent dextral shearing with that subvertical extension. So we can conclusively say that we have transpression in this zone. However, there's one more concept that we need to address: triclinic transpression. So up to this point, we've been talking about monoclinic transpression. So monoclinic transpression is transpression in which the pure shear component and the simple shear component share a common axis. In this case, the principal strain axis of the pure shear component is aligned with the secondary strain axis of the simple shear component. In triclinic transpression, none of the strain axes are aligned with one another. And in this case here, we're seeing in this example that I'm showing here, the pure shear component is inclined. Now, this means that the extrusion direction will also be inclined, and things like linear features such as mineral lineations will be oblique. So it's possible, but not always necessary, for the extrusion direction to be inclined, even while the simple shear is still parallel to those shear zone boundaries. So why do I bring up triclinic transpression? Well, we have the Zach outcrop. The Zach outcrop is very interesting in that it's located around 150 meters north of the Vigo outcrop, but is instead dominated by siltstones. So we've got siltstones, some banded iron formation here, and some quartz feldspar porphyry, but mostly siltstones. We have that same strong northwest striking subvertical at this point, early foliation, and we have all these indications of strain. However, we have a mineral lineation that is now oblique. It is moderate to shallowly plunging. Here we can see it being defined by the alignment of muscovite and biotite within a metamorphosed siltstone. And we also see that the early fold axes and those late fold axes are once again collinear with one another and collinear with that mineral stretching lineation. So once again, to show though, all the other structures observed on this outcrop are consistent with what we've seen across the rest of the deposit. So here we've got the bedding within that within the siltstone is isoclinally folded and transposed parallel to that early foliation. Here we have actually a quartz vein, which has been completely isoclinally folded by that early generation folding. This is the banded iron formation here, and this dashed line represents that early foliation. And we can see the asymmetric folding of it, the Z-shaped folding, indicative of that dextral shearing. And then finally here we've got that early generation folding actually being refolded by the late generation asymmetric folding, all within this same dextral transpressional event. And then finally, these dextral shear bands transecting an intermediate dike, and we have the boudinage and backwardation of that dike. So the only difference between the Zach outcrop and the other outcrops that we've seen is the change in the plunge of the lineation and the fold axes. So the first thing that somebody might say is, okay, well, why can't it be that we have a later dextral event or dextral shearing event that is superposed on top of this deformation? Well, what we can do is we can actually calculate what the simple shear direction was at this outcrop and the other outcrops and compare it. So that's what we did. So we calculate, what you can do is you can measure the orientation of the foliation and the shear bands where they intersect one another, and you can calculate the slip direction. And this was done not only with the Zach outcrop, but across the deposit. And what we found consistently is that the mean slip or shear direction is very shallow. It's 19 degrees towards the southeast. Now that moderately plunging lineation is consistently steeper, indicating that these linear features converged upon an orientation that is steeper than the simple shear component itself, indicating there was a component of pure shear. Now, how do we have triclinic transpression at one outcrop and what appears to be monoclinic transpression at another? Well, we can explain this with the concept of strain partitioning. So strain partitioning is essentially the partitioning of deformation into domains with different pure shear and simple shear ratios, or different pure shear and simple shear strain axes orientations. Strain domains often correspond with differences in rheology. So let's say a less competent sedimentary unit, like what we see at the Zach outcrop, will respond differently than a more competent quartz feldspar porphyry at the Vigo outcrop. So this may explain why less competent units or less competent rocks, like at the Zach outcrop, underwent oblique extrusion and possibly a larger simple shear component. To maintain kinematic compatibility, though, between these two different domains, you need to have what are called strain discontinuities between these different domains. And these are expressed as discrete faults or minor shear zones between these two different domains. All right, now that we are done with the intense, heavy portion of the structural interpretation, let's get into providing some brackets on when this deformation may have occurred. So this is our section on uranium, lead, zircon geochronology. So samples were collected, sent to ODM, zircon concentrates that were received were bulk mounted onto epoxy pucks and imaged on the SEM. Now, the backscatter electron and cathodoluminescence imaging of the sample zircons revealed that we had very, very small zircons, averaging around 50 microns on diameter, and they may be microfractured or contain inclusions, which is not great for dating. What we did then was we collected not only the uranium, thorium, lead data, but also trace element data. And using that trace element data, the resulting analyses were filtered using parameters to hopefully remove any analyses that we thought may be containing inclusions or affected by lead loss. So first, it was a 5% discordance filter, then filtering out for common lead and strontium to look for any analyses that may have lead loss. But then what was very fun was actually applying filters for calcium, which would indicate feldspar inclusions, for elevated titanium for titanium oxides, iron for iron oxides, and lanthanum for apatites. And the resulting analyses, interestingly, had high light rare earth element indices, which is a way of calculating and seeing if the analyses are relatively altered or unaltered. And these high indices indicated that these analyses were relatively unaltered. So where were the samples that we actually dated? First, we dated the Rice Lake outcrop. So this is a quartz feldspar porphyry that is at depth mineralized, and it is myelinitized, so this would provide a maximum age on deformation. Then we sampled and dated the felsic, it's an etheric felsic dike from the Inco outcrop, once again to provide a maximum age on deformation, but within the mafic domain. And then 3 syntectonic granites were dated from what's called the power line area, because of a power line. These syntectonic granites both intrude into strongly deformed mafic volcanics, but they themselves are weakly folded and contain a weak foliation, indicating that they were in place sin deformation, but likely within those last stages of deformation. So this tells us that deformation must at least locally outdate this, this age. So we have an age of 2712 plus or minus 2.2 million years for that quartz feldspar porphyry, which is actually within error of dates by Jack Simmons, where we have an age of 2710.2 plus or minus 1.2 million years. And interestingly enough, there was additional dating done at the OGS, not of the quartz feldspar porphyry, but of an aetheric felsic porphyry that was also mineralized. They got an age of 2716.2 plus or minus 1.8 million years. So we're really within that same ballpark, not within error, but still within that same sequence. We've got ages of the Inco outcrop at 2714.2 plus or minus 2.9 million years. And then our three ages of the granites and the Powerline outcrop are all within error of one another. And our youngest age was 2692.4 plus or minus 4.5 million years, provides our age at which deformation must locally outlast. And here is our data presented as a chart. So you can see the actual individual analyses that contributed to those ages. Here you have in blue is the quartz feldspar porphyry. The age is used to calculate it. The felsic dike at the Inco outcrop. And then finally our syntectonic granites. Now, let's put all of this into the regional context. So this is a time age diagram of the Red Lake Greenstone Belt. Now, as you can see, the Mesoarchean is a little bit squished, mostly because it doesn't outcrop on this deposit, hence why it is not highlighted. Instead, we're going to look more at this Neoarchean part of the Red Lake Greenstone Belt. So here you see this top line is volcanism. We can see the Confederation and Graves assemblages, which are considerably, Confederation is what I mentioned earlier. It was previously thought to be for the felsic domain. Then we have the sedimentary unit. So we've got the Huston, which is previously assumed to be the youngest sediments within the Red Lake Greenstone Belt, but we actually have now what I'm terming the Great Bear sequence. This is based on dating by Jack Simmons, which will come out soon. And it is, as we can see, considerably younger than previously assumed in the area. We have the Plutonism that is seen across the Red Lake Greenstone Belt. And finally, this last line is deformation and metamorphism. D1 being deformation that is seen in Mesoarchean and Confederation aged rocks, D2 being the main deformation event in the Red Lake Greenstone Belt. D3 is often considered to be coplanar with D2 deformation, and considerably less is understood about D3 deformation in the Red Lake Greenstone Belt. And then finally, D4 is late brittle deformation, which is poorly constrained in terms of timing. Now, once we add on our ages here, the quartz feldspar porphyry, the aetheric felsic dike, and our syntectonic granites, we can see that structures along that LP deformation zone had to have formed after 2712.3 and before 2692 or locally outlasting 2692.4 million years. So this means that D3 or that the LP deformation zone is the local expression of D3 deformation in the Red Lake Greenstone Belt. And this also means that that D3 deformation and what we're seeing as the LP deformation zone is the last increment of regional shortening associated with the Uchian phase of the Knorr orogeny. So now finally, after all that, let's get into the structural controls on gold mineralization. So this is just a perspective view of the leapfrog model where you can see just the approximate locations of the LP zone, limb, and hinge zones, so that when we look in 3D, we know where we are. So as you can see, this is a 3D ore body shape. It is of the 0.5 gram per ton grade shell, but of course it's mostly just to show us the locations of the ore bodies and the extent. So let's get into what this mineralization really looks like. So for the LP zone, mineralization is hosted within transposed gray diffuse quartz veins. These veins are parallel to the main foliation within the deformation zone, and gold is associated with pyrite, pyrrhotite, sphalerite, arsenopyrite, usually occurring within the veins, on the margins, or within the host rock adjacent to these veins. The ore body itself plunges steeply 70 degrees towards the northwest. The hinge zone is very similar in that you have this white to gray quartz veining. It's quartz carbonate veining. It is once again folded or transposed parallel to that dominant foliation, and is often considered, they call it axial planar quartz veins, but they have been folded so they are now planar to that dominant fabric. Gold is once again associated with a similar mineral assemblage occurring often on the margins of these veins. And lastly, we have the limb zone. And the limb zone is hosted within this argillite. It's often called sulfosilicate replacement. It is these diffuse quartz veins and sometimes associated also silicification of the argillite. We have high concentrations of pyrrhotite, gold occurring on the margins. So what we're seeing time and time again is that gold-bearing quartz veins across the LP, limb, and hinge zones have all been deformed by D3 deformation. So here what we see is 3 examples of veins in the LP zone. We can see veins that have been transposed parallel to that foliation, being folded axioplanar, or with the dominant foliation being axioplanar to these folds. And even when they may seem oblique, we can actually see that they have been folded by that deformation. These here are cross-polarized light images of those veins. And we can see that the vein quartz has been intensely recrystallized. And then once we actually look using backscatter electron imaging, we can see that the gold itself has been deformed by that deformation. What's really important to note as well is that there are no thick mineralized shear veins on the property. So all of this suggests that gold mineralization must predate and be reoriented by D3 deformation. Now, this is substantiated by the actual structural controls that we see on the gold. The strike and dip of the LP ore body is consistently parallel to the dominant foliation throughout the LP deformation zone. Mineralized quartz veins are tight to isoclinally folded, parallel to that, or axoplanar to this dominant foliation. And finally, the ore body itself is steeply plunging to the northwest, which is collinear with that steeply plunging mineral stretching lineation, indicating that D3 transpression has reoriented and controlled the plunge of the ore body. So let's put all of this into the regional context now. So this is mineralization at the bottom now. We can see high-grade mineralization at the Gold Madsen and remobilization. So we know that gold had to, we know that the quartz feldspar porphyry here is mineralized, and that gold mineralization must predate peak D3 deformation. So this means that gold mineralization must have occurred as either orogenic gold associated with the burial of that felsic volcanosedimentary package, perhaps with D2 extending slightly further along in the southern parts of the Red Lake Greenstone Belt than previously established, or that this is intrusion or synvolcanic related gold associated with that felsic magmatism, perhaps something similar to what is seen at Rainy River or Goliath, which are contemporaneous deposits. Now, some quick conclusions. The structures observed across the Great Bear property suggest that deformation resulted from a continuous dextral transpressional event. This transpressional event is the local expression of regional D3 deformation in the Red Lake Greenstone Belt. Deformation occurred after 2710.2. This is the age, the TIMS age provided by Jack Simmons, and it locally outlasted 2692.4 plus or minus 4.5 million years. These gold-bearing quartz carbonate veins were in place prior to D3 transpression, and then were subsequently deformed by that D3 event and metamorphosed. Finally, the ore zones themselves are steeply dipping, northwest striking, and steeply plunging, indicating that they were transposed and stretched parallel to the dominant foliation and lineation in the transpression zone. And finally, gold mineralization represents a new event that postdates main mineralization at the Red Lake Greenstone Belt. All right, so quick acknowledgements. First off, thank you, Bruno, for everything, for being a wealth of knowledge. I've learned more in the last 2 years than I think I've learned in the rest of my life. So thank you so much. Thank you, Jack. I would not have been able to probably get through all this without your support. Thank you, Stephanie, for all of your support throughout this entire process. It is much appreciated. Thank you, Ross, for, despite not being on my committee, being there throughout the entire process. It is much appreciated. Thank you, Veland and Jolene. You guys have been the best roommates in the field, and thank you for dealing with my endless questions. And a huge thank you to everyone at Kinross, especially Hannah and Dana, for being excellent friends when I was there, and also just for being so responsive and providing all the data that I needed to do this study. Thank you to Juan Carlos and Graham Long for all of your help and your support in getting me to do this project. And a massive thank you to the entire Kinross survey team, without whom I'm pretty sure I would still be stuck somewhere in the bush in a mud pit. And then a huge thank you to everyone at the university, everyone on the SCG. We've had some amazing trips going to Chile, Nevada, Brazil. Like, this has been an incredible 2 years. Thank you to everyone in the LU Run Club for my mental health. Thank you to all my amazing friends in the department and around the world. And a huge thank you to my office mate and friend Jermaine for putting up with me for 2 years. Lastly, thank you, Chris, for your patience and support, and to my family for believing in me. Thanks, Mom. That's it. It was roughly on time.
Didn't get any of what you said, but it was a very good presentation.
Okay, cool.
Okay, so